Good evening, ladies and gentlemen. Welcome back to Reference Point. I'm your host, Dave Coker-Hook, and with me again is my friend and very learned individual, Mr. Jordan Mackauer. We've been talking about astronomical things, space, telescopes, the creation of the universe, our star system, etc., etc. Jordan, welcome back to Reference Point. Glad you're here.
Thank you. Glad to be here.
You are an educator, you're an author, you're a researcher, you're a barbershop singer, you do all kinds of things, and I really appreciate that you have taken some time to sit down and chat with me here, so thank you.
Always a pleasure to talk with you.
So we ended off at the last show talking about the different kinds of telescopes that we use in order to capture stellar information. And the thing we ended up with at the end, we were discussing radio telescopes, and I thought that was really very interesting. In that I didn't know exactly how that worked. I thought they were just trying to capture, sound stuff for listen to see what was going on, what kind of tones the universe is generating, but it's a lot more than that. They're actually able to generate an image based on the information they capture, right? And so could you explain again how they work?
Okay, let's talk first. The easiest one to talk about is an optical telescope. And the simplest optical telescope was actually discovered before Galileo. By a couple of kids playing in a optician's store, playing around with lenses. And they discovered that with the right combination of lenses, two lenses, one of a stronger power than the other, you could get a telescopic effect. And then it was a toy by the time Galileo got it, and he used it for astronomy. So there's the optical telescope, which is a lens at that time, which with gathered and magnified light to a focal point that was enlarged by yet another lens, a magnifying lens. And since that time, other optical telescopes were developed.
Sure.
Ones that use mirrors to gather the light, send it to a mirror in the tube of the telescope out to where you got that magnifying lens.
It's like you see this sort of thing at observatories that like up Mount Hamilton has an observatory here in our area, or Griffith Observatory down in Los Angeles area, right? So that's that kind of optical side, whether it's captured from the reflection of the mirrors or direct lensing. Okay, get that.
Can you imagine a telescope so big, and this exists, that a person climbs inside of it to sit where that light comes to a focus?
No, no.
That exists. A
wow.
200-inch telescope.
Wow.
So optical telescopes. Okay, now the radio telescope uses, instead of a lens, it could be chicken wire. It's metal, and it could be shaped as a dish that is curved slightly to, again, bring that energy to a focal point where there is a device that will decode that information, send it to the computer, which will further decode it, and then to a place where that information can be printed out. It can be printed out as a graph. It can be printed out as an image.
Okay.
Beyond that,
so I'm going to stop you there for a second,
ahead.
because what this tells me, or it says to me, if they're able to capture that energy, okay, that everything that is emitting some kind of energy.
Yeah, our sun emits radio energy. You could use your FM radio, whatever it is, and put an antenna, a piece of wire, on the south side of a building. And as the sun passes south here in the northern hemisphere, it will transmit radio energy to that antenna, And if your FM radio is tuned to a blank spot on the dial, you'll hear a hiss, which is from the energy from the sun. But the sun isn't the only thing in our solar system that produces radio energy. Jupiter also produces radio energy. Of course, not to the extent that the sun does. But stars, in the process of forming the elements and making radiant energy, also produce radio energy.
So you're getting different you're getting different pieces of information from the radio telescope than you are from one of the other types of telescope that capture either infrared or ultraviolet or optical. Okay.
Yeah.
And so I'm deducing that the combination of these data points or these bodies of information help to be able to ascertain some of the things that they're saying that they've identified and discovered. Like you were talking about something a little bit earlier during the break about a recent observation of a stellar system that people were just like, oh my goodness, I didn't realize that could be. So I'm assuming that that's part of the overall picture of weaving all this data together.
All of the electromagnetic spectrum, of which you have a diagram, all of that is sending energy our way, and with the proper devices, we put together those puzzle pieces to understand and to make a model of what is really going on there. When you look at the pictures that the James Webb Space Telescope produces, and you see these little dots, that's an entire galaxy. That's hundreds of billions of stars in that little dot.
Yeah.
And we can't resolve that unless you had something that would be huge to collect all that data.
Right.
But you could take all the pieces of the information and put together that concept.
And that is interesting because they were able to tell how do I want to say this? What makes up certain stellar objects by virtue of this spectrographic determinations and things, which is really okay. So that's fascinating. I want to call up an image now, image number 5 on my handy dandy little list here, because this was an image from the James Webb Space Telescope, and you've got these curved looking items and things like that, and it's also speaks to this concept, I think, of gravitational lensing as well, which is a whole other thing that was an area of new knowledge to me not too terribly long ago, that a thing could be, and this goes back to our friend Albert, Mr. Einstein, and how mass and gravity can bend light and stuff like that. But this image is really interesting because these stellar objects that they're seeing out there are like way far away. And what causes it to look this kind of unusual shape? It's not like when we see shapes of galaxies, we see, it's a spiral galaxy, it's a this, it's a that, blah, blah. These things look like stuff that you would see in a fun house when the mirrors and how does that happen?
All right, backing up a tiny bit, there are 3 basic shapes to a galaxy, and they're probably a lot more definitive breakdowns. There's a galaxy that's shaped like a huge lens, and the galaxy will have a bulge in the center. It'll thin out to the sides, and there'll be bunches of stars above and below it, and bunches of stars in the spiral arms in that lenticular type of galaxy. Then there's a galaxy that's like a ball. Everything is compact. Then there's another galaxy that has been twisted by the forces of other galaxies around it, so it has no particular shape. So you've got the lenticular or spiral, you've got the elliptical, and you've got the irregular types of galaxies.
Right.
Now, what you're looking at In that picture, the really one of the first pictures that was shown from the James Webb Telescope, and you see that curvature. They say, all right, well that's caused by gravitational lensing, and believe it or not, that concept was first put out by Johann Georg von Soldner in 1804.
That's quite the name.
It is.
We have kind of a graph. Would this graphic be appropriate to be talking about relative to that?
No, not yet.
Not yet. Okay.
Back in those days, they were dealing with. They thought everything was made of particles.
Right.
So when we got to Einstein, and we are talking about light, which can exist as depends on the type of light, which can exist as a wave, or can exist as a stream of particle, or a wavicle.
Right.
Then Einstein predicted that with a mass great enough, light from a distant object could be bent by space-time, is what he called it, and be visible. And it wasn't until 1919.
Be something that was on the opposite side of whatever this mass object is that you can't see.
Right.
Would be visible based on the theory.
So let's pretend that this is the sun, just as an object.
Yeah.
When the moon would block the sun, you should be able to see a star behind the sun. In fact, well, you can't see it during the daytime anyhow, because the sun's blocking it. But what Einstein suggested was that because of the mass of the sun, that light and space-time are bent so that it becomes visible. And now you could look at that picture of gravitational lensing.
That would be image number 6.
And that shows a simplified version of the bending of space-time by a massive object. Now here's the problem. People think about that gravitational lensing. They think that the lens, it looks like this.
Yeah.
But
no.
What if the lens, the galaxy, and the unseen matter behind it, which is mostly responsible for the bending, is tilted? And so that's why we see the curve, the outside of the dark matter, bending that, and so we have distorted a distant galaxy for whatever shape it's actually in to look like a curve. Or they call that an Einstein ring if it's completely circular.
Very cool. All right.
More than you wanted to know.
No, I would not say that it's more. It actually fills in some gaps. So as we see that, even though we're getting that visual distortion because of the lensing effect, etc., based on the spectrographic assessment that we were talking about earlier, they're still able to ascertain what kind of activity or elements are within that object that they're seeing. And as you were saying earlier, with whether the red shift or the ultraviolet shift, whether it's coming toward you or away from you and stuff like that, right?
Everything except the stuff in our immediate neighborhood is moving away from each other and from us. Everything that we can perceive. And the spectroscope, the tool that allows us to see the light and to analyze it, we can tell how fast they're going, and because of the speed, we can tell how far away they are, and we can tell if they're rotating, we can tell if the object is tilted or not. Of course, we can get the chemical composition of the atmosphere. We can detect distant planet, exoplanets, and the atmosphere of those planets with the James Webb Telescope. It's a new ball game. It's getting us to, with a brand new tool, we can tell so much.
That's really awesome.
We keep developing more tools, and astronomy keeps changing.
Yeah, no, I think that's phenomenal. I do want to get in the last, I guess, 10 or 12 minutes that we have here. I want to talk about this topic of dark matter, dark energy, because it's one of those things that, as a layman, you hear and you read about it and you go, I have no clue what the hell they're talking about, okay? But the concept, as I fundamentally understand it, the basics of my understanding, is that there has to be something else that we are not perceiving with the instrumentation that we currently have or have had, because the way certain things are behaving or certain activity that is discernible would indicate there's something else there in a way of mass or energy that is creating the result that we're observing. I don't know if that's a rational way of saying it, but that's kind of what my understanding is, and I'm guessing a lot of the folks out there in viewer land are thinking as well.
Okay. To get to what you're talking about, again, I've got to back up a little bit about the concept of gravity. So, gravitational force, you need a lot of matter, but even the tiniest amount of matter will attract another amount of matter toward it.
Mm-hmm.
So we live on a massive planet, 7,926 miles in diameter through the equator.
Mm-hmm.
In order for us to launch a rocket into space, we have to exceed a speed of 18,000 miles an hour.
Right.
In order for that to go into a bigger orbit, it's got to go 21,000 miles per hour.
Mm-hmm.
And that rocket is being pulled back by the Earth. In fact, the rocket is also pulling the Earth to a small degree.
Right.
So the planets in our solar system are being pulled by the sun.
Right.
Closer planets, Mercury, goes around because of the intense pull of gravity in 88 days. Pluto, at a distance of, let's see, over approximately 39 billion miles.
Okay.
Takes 240 years to make an orbit, but it's still being pulled by the force of gravity of the sun.
Mm-hmm.
So you expect, when you're looking at a galaxy, to follow these same rules. But things on the outside of our galaxy
Mm-hmm.
are moving faster than they should.
Based on that concept,
based on
what we understood at the time.
Beyond the Newtonian gravitational principle.
Okay.
Something's got to be pulling it. And what's pulling it is conjectured to be, and can be proven to be, dark matter and dark energy. That it's out there causing this acceleration of objects at the periphery of our galaxy.
I think the way that I hadn't heard it expressed before is something must be pulling it.
Right.
Because I get, when you, and even, when I was a kid and you're studying basic science, I said, the laws of Newton, energy, things fall, gravity, blah, blah, blah. And you say, okay, cool, that's kind of fine. But you don't think about the fact that you are being pulled, okay? And the mass of the sun is pulling, but then something, so I get that. I hadn't considered that there needs to be something, if as we are able to determine the galaxies and the other body items of space are moving away, something has to be pulling at them to cause them to want to move in the direction that they're moving in. They don't just kind of go.
Well, they could be moving because space is expanding.
Mm.
And I find that concept really difficult to get. It's a lot easier to say, okay, well, here's a massive object, and if I'm close to it, the gravitational pull is greater. If I'm further, gravitational pull is less.
All right.
So you'd actually weigh 1% less at the north and south poles. No, pardon me. You weigh less at the equator than you would at the north and south poles,
Mm-hmm.
because of the bulge of the Earth.
Oh, right, yeah.
Okay, but again, things are in motion faster than they should be, based only on Newtonian mechanics.
So how do they, what have they used to ascertain the existence of this concept of dark matter, dark energy, other than the fact that they think that things are moving faster than they should? What is there a way to measure?
The only way that you can tell the action of this seemingly inert substance is by the effect it has on its surroundings.
Okay.
So the gravitational lensing is used as one type of proof that dark matter is out there. The motion that I talked about several times now in a galaxy, or the outermost stars, is another proof of a greater substance around that. And if I haven't mentioned it before, there's only 5% of the universe that is optically or detectable, visible. The rest is the dark matter that you can only tell its presence by what it does to the surroundings.
Yeah, the tendency is to think that, yeah, we got these massive distances between objects, and there's nothing, the sun, Pluto, whatever, and there's nothing in between it. Well, in the solar system, we know there's stuff, but it's like we look at the Milky Way galaxy, and the next one out, Andromeda, or wherever it is like way out there, okay? And you think that there's nothing in between. But what you're saying is that, no, there's a lot of stuff in between.
Right,
we
dark
just
matter.
don't have a way of observing it. We observe its impact.
Correct.
But we don't have the instrumentation yet to be able to observe it directly.
Correct.
Okay, so where does that leave us?
It leaves us with problems that will be solved by future generations, and minds that will come up with ways to measure things that we haven't thought about measuring yet. It'll be like things that Johann Georg von Soldner couldn't conceive of,
Right.
because they were working on a particular theory of matter back then.
Right.
And now we are in a different, with greater technology, we have a greater view of the universe that's around us, the physical and the energetic universe.
I think what you just said is actually probably one of the more significant things that you've said today, which is that what was determined by the existing technology back 100, 200, 400 years ago was based on what they were able to discern at the time with the materials and the equipment that they have. Science continues to evolve. We get to points where we're able to understand things that we couldn't understand before because we can see them or detect them or figure them out, or we've come up with instrumentation to help us see things, okay? I mean, look at what the Large Hadron Collider does to be able to determine some of these other small particles that were theorized, and now they're able to discern. We didn't have a piece of equipment that could do that before. But now that we have these things, we can say, oh, well, and then you can extrapolate from there. So I think it's really significant and important that what you said about we're able to move everything forward, move our species forward, move the whole eco-environment forward, and that's fantastic. Jordan, we're down at a point where I think we're just about out of time again. This was a very quick conversation. I'm trying to look very quickly to see if there's anything else that I felt that I really wanted to touch on that we haven't touched on, but I think we've pretty much got most of it. Thank you for being here. You mentioned that there might be a talk that you're giving later in the month of May here, right?
I'm a member of the San Jose Astronomical Association, and they sponsor in-town star parties. They're located in Campbell, and they're going to, in theory, if the weather allows, they're going to have a star party this coming Friday.
This Friday the 12th?
This Friday the 12th, and I will be talking to a school in Cupertino, answering questions from their students on a date later on in this month. And I don't want to mention that because I don't want to get...
It's private for them.
Right.
How often do they have these public events? You mentioned that the one down in
Campbell.
Campbell.
Right. Roughly once a month. They have to avoid the full moon because it whitens the sky and makes it really difficult. They've got to avoid the cloudiness of the weather.
Well, yeah, of course.
So once a month.
Once a month.
And if you go to SJAA, San Jose Astronomical Association, you can find out their schedule. You could join.
Is that sjaa.org or .com?
It isn't commercial, so it probably is .org. Okay. However, if you just type in San Jose Astronomical Association, it'll give you their website.
Google will find it for you.
Correct.
Okay, well, really cool. Thank you, my friend. It's been a pleasure to have you here. This has been a lot of fun for me, and I feel like I've absorbed a certain amount of that knowledge, so thank you for that. Ladies and gentlemen, I hope you've enjoyed this series of conversations as well, because this whole thing about what's going on in the universe is fascinating. Don't forget, you can send your questions about anything that we've talked about here to info@referencepointtv.com. We'll get your questions answered. Jordan's really good about that, and he makes sure that they're thorough too, which I appreciate, my friend. So, Jordan, thank you very much. Appreciate your being here, and ladies and gentlemen, we'll see you next time on Reference Point.